P-type semiconductor. Today we shall study about P-type semiconductor. This is obtained when Si, silicon iron or germanium is doped with a travalent impurity like aluminum, boron, indium, etc. The dopant has one valence electron, less than Si or G, and so this atom can form covalent bonds with neighboring three Si atoms, but does not have any electron to offer to the fourth Si atom. So the bond between the fourth neighbor and the travalent atom has a vacancy or a hole as shown in figure 1. Since the neighboring Si atom in the lattice bonds an electron in place of a hole, an electron in the outer orbit of an atom in the neighborhood may jump to fill this vacancy, leaving a vacancy or hole at its own side. Thus the hole is available for conduction. Note that the travalent for an atom becomes effectively negatively charged when it shares 4 electrons with neighboring silicon atom. Therefore, the dopant atom of P-type material can be treated as core of one negative charge along with its associated hole as shown in figure 1. It is obvious that one acceptor atom gives one hole. These holes in addition to intrinsically generated holes, while the source of conduction electrons is only intrinsic generation. Thus, for such a material, the holes are the majority carriers and electrons are minority carriers. Therefore, extrinsic semiconductors doped with travalent impurity are called P-type semiconductors. For P-type semiconductors, the recombination process will reduce the number Ni of the intrinsically generated electrons to Ni. We have for P-type semiconductors NH is greater than Ne. Note that the crystal maintains an overall charge. Neutrality as the charge of additional charge carriers is just equal and opposite to that of the ionized cores in the lattice. In extrinsic semiconductor, because of the abundance of majority current carriers, the minority carriers produced thermally have more chance of meeting majority carriers and thus getting destroyed. Hence, the dopant by adding a large number of current carriers of one type, which become the majority carriers, indirectly helps to reduce the intrinsic concentration of minority carriers. The semiconductor's energy band structure is affected by doping. In the case extrinsic semiconductor, additional energy states due to donor impurities ED and acceptor impurities EA also exist. In the energy band diagram of N-type silicon semiconductor, the donor energy level ED is slightly below the bottom EC of the conduction band and electrons from the level move to the conduction band with very small supply of energy. At room temperature, most of the donor atoms get ionized but very low. Near about 10 to the power minus 12 atoms of silicon get ionized. So the conduction band will have most electrons coming from the donor impurities as shown in figure 1a. Similarly, for P-type semiconductor, the acceptor energy level EA is slightly above the top EV of the valence band as shown in figure 1b. Now, with very small supply of energy, an electron from the valence band can jump to the level E and ionize the acceptor negatively. At room temperature, most of the acceptor atom gets ionized, leaving holes in the valence band. Thus, at room temperature, the density of holes in the valence band is predominantly due to the impurity in the extrinsic semiconductor. The electron and hole concentration in a semiconductor in thermal equilibrium is given by NENS power Ni square. Though the above description is grossly approximate and hypothetical, it helps in understanding the difference between metals, insulators, and semiconductors in a sample manner. The difference in the resistivity of carbon, silicon, and germanium depends upon the energy gap between their conduction and valence bands for C, Si, and G. The energy gaps are 5.4 electron volt, 1.1 electron volt, and 0.7 electron volt on it. Sn is also a group 4 element. It is a metal because the energy gap in its case is 0 electron volt, as shown in the figure. Now, p-n junction. p-n junction formation. Consider a thin p-type silicon PSI semiconductor wafer. By adding precisely a small quantity of pentavalent impurity part of the PSI wafer can be converted into NSI. There are several processes by which a semiconductor can be formed. The wafer now contains P region and N region and a metallurgical junction between P and N region. The important processes occur during the formation of a p-n junction: diffusion and drift. We know that in an n-type semiconductor, the concentration of electrons, number of electrons per unit volume, is more compared to the concentration of holes. Similarly, in a p-type semiconductor, the concentration of holes is more than the concentration of electrons. During the formation of p-n junction, and due to the concentration gradient across P and N sides, hole diffuse from P side to N side, and electron diffuse from N side to P side. This motion of charge carriers gives rise to diffusion current across the junction. Now, when an electron diffuses from N to P, it leaves behind an ionized donor on N side. This ionized donor is immobile as it is bonded to the surrounding atoms as the electrons continue to diffuse from N to P. A layer of positive charge on N side of the junction is developed. Similarly, when a hole diffuses from P to N due to the concentration gradient, it leaves behind an ionized receptor which is immobile. As the holes continue to diffuse, a layer of negative charge on the P side of the junction is developed. This space charge region on either side of the junction together is known as depletion region. As the electrons and holes taking part in the initial movement across the junction depleted, the region of its free charge, as shown in the figure 1, the thickness of the depletion region is of the order of 1/10 of a micrometer due to the positive space charge region on N side of the junction and negative space charge on P side of the junction. An electron field directed from positive charge towards negative charge develops. Due to this field, an electron on P side of junction moves to the N side and a hole on N side of the junction moves to the P side. The motion of a charge carriers due to electric field is called drift. Thus, a drift current which is opposite in direction to the diffusion current starts. Initially, diffusion current is large and drift current is small. As the diffusion process continues, the space charge regions on either side of the junction extend, thus increasing the electric field strength and so drift current. This process continues until the diffusion current equals the drift current. Thus, a p-n junction is formed. In a p-n junction under equilibrium, there is no net current. Since the potential tends to prevent the movement of electron from the n region into the p region, it is often called a barrier potential, as shown in figure 1 and figure A and B.